This is the screencast for section 4.3, example 3. We're going to find points of inflection. Points of inflection are where the concavity changes. So at those points of inflection, there's actually an instant moment where there's no concavity. It's not concave up, it's not concave down, the concavity is changing. So find points of inflection. So we're going to find all points of inflection of the graph of y equals e to the negative x squared. So you may predict we're going to use the second derivative. Since the second derivative tests for concavity, where the second derivative changes signs, we're going to find an inflection point. So when the second derivative changes from positive to negative or negative to positive, we'll have a point of inflection. So step 1, find the first and second derivative. What a mess. I'm definitely going to have to use chain rule here. And now to find the second derivative, I'm going to have to use product rule. But then when taking the derivative of the piece of the product e to the negative x squared, I'm going to have to use the chain rule again. And then I'll simplify. Now, although this is simplified, this isn't the best way to find the zeros or the values of x that make the second derivative undefined, the critical values. So I'm going to change this so that I have this negative exponent, and I'm going to kind of factor out a common factor and create a denominator so I can get a better idea of what will make this 0 or undefined. So now I see there's actually nothing that's going to make the denominator 0. The denominator will always be positive, but I can find out what's going to make 1 minus 2x squared 0. And I got that it was plus or minus the square root of 1/2, but if you rationalize the denominator, it's square root 2 over 2. So now I can test that on a number line of the second derivative. My two critical values are negative square root 2 over 2 and positive square root 2 over 2. So I'll test those three intervals. And now I have the ability to identify the inflection points. It turns out that both of those critical values were in fact inflection points. So now you don't get an inflection point if it stayed positive or it stayed negative, but because the sign of the second derivative changes at both of those critical values, you do get inflection points at both x equals negative square root 2 over 2 and positive square root 2 over 2. The now try problem number 13 is similar. We're going to find the inflection points. We even have a similar problem, so I'm going to dive right in and find the first and second derivative. I'm not going to have to use the chain rule in here, but I'm going to need to use the product rule. Now in finding the second derivative, I can see that e to the x is going to stay the same, but I'll have to use the product rule for the second part. Simplified, and then again I'm trying to find the critical values, so I want to factor out e to the x so I can find the x values that make this 0 or undefined. And e to the x will never be 0 or undefined, but 2 plus x will be 0 if x equals negative 2. So negative 2 is a critical point. So I put negative 2 down as a critical value on a number line for y double prime and test y double prime in both of those intervals. So you can see that the y double prime changes signs at the critical value negative 2. So there is an inflection point in y at x equals negative 2. Now you could also plug in negative 2 to find out what the actual y value is there. So I do see that there is an inflection point at 2, comma, negative 2 e to the negative 2, and that's an inflection point of y because y double prime changes signs. Specifically, y double prime is changing from concave down to concave up, so it might be doing something like this. I don't know.